All right, this is AP BC Calculus. We're doing a BC only section. This is Unit 10, Section 15. We are representing functions as power series. So this is basically more of that sine, cosine, e to the x Maclaurin stuff. So let's start with E1. So we have this integral representation from 0 to x of cosine of t cubed dt. We're asked to write the series for this expression, including the first three non-zero terms and the general term. So basically what we're going to need to do is we're going to need to look at this integrand. And we're going to have to take the thing that we memorized, right? So the thing that we memorized is that cosine of x is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. So basically all the even powers of x. So x to the 2n over this 2n factorial with this negative 1 alternating, right? Okay. I'm going to take that memorized series. I'm then going to apply it and realize that the integrand, so this cosine of t cubed, right, should be this exact series but with a t cubed anywhere I see an x. So I'm going to get a 1 minus t cubed squared would be t to the 6th over a 2 factorial, right? Plus t cubed to the 4th would be a t to the 12th over a 4 factorial, right? Plus negative 1 to the n. And then instead of being an x to the 2n, it's a t cubed to the 2n, which would be a t to the 6n over this 2n factorial. Okay, so now the trick is that I don't want that though, right? I want the integrand of that, right? I want the value when I integrate that. So when I integrate that, if I integrate this thing term by term, right, what's going to happen is that I'm going to up the power by 1, divide by the new power, right? And I'm going to do that for every single term, right? So up this power by 1, well, that was a t to the 0, so now it's t to the first. So I'm going to get that this is going to be a t, right? Minus, this becomes a t to the 7th, so t to the 7th over a 2 factorial times a 7, which we'll deal with in a sec, right? Plus, this becomes a t to the 13th, so t to the 13th over a 4 factorial times a 13, which we'll deal with in a second, plus . When I up the power by 1, this becomes a t to the 6n plus 1. And here I have this 2n factorial times the quantity 6n plus 1. And the trick is, and I'm kind of a little low on space here, but I'm evaluating that from 0 to x. Well, when I plug in 0, all of these are gone, right? When I plug in 0, they all have t's. They're all going to be gone. So this just ends up being what happens when I plug in x's. So it's going to be an x minus an x to the 7th over, and if you wanted to do 2 times 7, that's fine. You certainly could. You could make it a 14. That's a reasonable expectation. So you could make 2 factorial times a 7 into a 14 if you want, right? I'm going to argue it's probably not a reasonable expectation for you to make this 24 times 13 into anything other than a 24 times 13. You could, but it's not really worth it. So you could probably write it as 24 times 13. It's not likely on a non-calculator section that it's required that you actually find the value. Right? On a non-calculator section, it is not likely that they're going to make you do 24 times 13. They could, but it's not likely. It's probably fine to leave it as a 4 factorial times a 13 or as a 24 times a 13. So I was asked for the first 3, right? First 3 non-zero terms, which we did. And then the general term is just going to be this term, but with an x instead of a t. So plus negative 1 to the n, x to the 6n plus 1 over a 2n factorial times a 6n plus 1. And that's it. And that's what I was asked to find. So notice that there's multiple, it was one question, but I actually had to do 3 things. I needed to think of the generic series for cosine, and I don't necessarily have to write it down. Sometimes an AP free response will actually ask you to do that. They'll actually say, what's the first 3 terms and the general term for cosine of x? Then I had to plug it in for cosine of t cubed and figure out what that would be, and then I had to integrate on a term-by-term basis. All right, so you're going to go ahead and try another one. You're going to try e to the t squared dt. Oh, it is worth noting, this is a thing that you couldn't integrate by yourself. You cannot easily integrate cosine of t cubed dt because it would be u sub, but there's no t squared on the outside. It's pretty complicated. So the same thing here, we're going to integrate, right? So the steps are, first, I need to look at the basic memorized function, right? The basic e to the x function, right, is just a 1 plus an x squared over 2 factorial plus dot, 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 x to the n over n factorial, right? The second thing I need to do is I need to take that basic function and write what's inside the integrand. So e to the t squared is this same function, but a t squared everywhere I found an x. So 1 plus t squared squared is going to be t to the 4th over 2 factorial plus dot, 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 dot. T squared to the n would be t to the 2n, right, over n factorial plus dot, 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 right? Now I need to take and actually integrate that, right? So that's my third step. My third step is to integrate that thing. And when I do, right, I'm going to integrate term by term. So when I integrate 1, I get a t, right? When I integrate t squared, I did a t cubed over 3. When I integrate t to the 4th, I get a t to the 5th, right, over, and then there was a 2 factorial times that 5, right, plus dot, 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 dot. When I up the power by 1, so this is t to the 2n plus 1, I'm going to divide by that new power. So I have an n factorial and a 2n plus 1 plus dot, 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 and I'm evaluating from 0 to x. Well, when I plug in zeros for all the t's, they're just gone, right? So I'm going to get, when I plug in the 0, 0, 0, 0, 0, so that's all gone. So I just get that this is an x plus an x cubed over 3 plus an x to the 5th over, and if you want to make this a 10, you certainly could. A 2 factorial is just a 2, so if you want to make that 10, it's fine. You don't necessarily have to simplify it, and then this is going to be an x to the 2n plus 1 over n factorial times this 2n plus 1, dot, 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 dot. And there's my first 3 terms and my general term, right? Make sure you follow the instructions, because you're going to also notice how I very clearly went out of my way to make sure I labeled which function is which, right? I clearly labeled that this was the basic e to the x, that this was e to the t squared, and that this was the integral I was trying to find. Make sure you label functions. Don't just throw out a series and not have it equal to anything. It's very unclear, and as you'll notice, there were 3 separate series in this answer. I had to give the basic one so that it was clear what I was using. I had to adapt that to be the e to the t squared, and then I had to do the integration. All right, so this is f. We're going to write the series for f prime of x, including the first 3 non-zero terms and the general term. So there's 2 ways you can do this, okay? Option 1 is to just straight up differentiate first, right? Option 1 is to say, hey, I'm going to just go ahead and differentiate first. So f prime of x should be the sum from n is 0 to infinity of if it helps you, you can treat this as this is your coefficient, right? And then this is the power of x, right? So I would drop the power down and then lower the power by 1. And if you want to do that, you could just go ahead and do that first, and then you could write out your series. You could start plugging in, you could start by plugging in n is 0. If you plug in n is 0, you're going to get 0, right? So when you plug in n is 0, you're going to get 0, right? When you plug in n is 1, you're going to get a 3 over a 2 factorial, right? X to the 2nd, right? When you plug in n is 1, right? When you plug in n is 2, you're going to get a 6 over a 3 factorial. X to the, we're plugging in 1, 2, 3, so that would be 8, right? Because it would be 9 minus 1, right? And I was asked for the first 3 non-zero terms, so the next one would be, so I plugged in n is 0 and got a 0. I got an n is 1, I got this. When I plugged in n is 2, I got this. When I plug in n is 3, I'm going to get a 9 over a 4 factorial. X to the, oh, sorry, I plugged in n is 2 here. This is a 5, my bad. See, this is why it's helpful to write what you plug in, because that's a 6 minus 1, and this one's going to be an 8, right? Plus dot, 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 and then I already have my nth term. It's 3n over n plus 1 factorial x to the 3n minus 1, and that's fine. That's one way to do it, and you could certainly do it that way, okay? So one way to do it is to differentiate this thing first, right? So that's fine. And if I did that, right, if I clean this up a little bit, my first 3 non-zero terms, I can ignore this guy, are 3 halves x squared. This is a 6 over 6, so I could probably just write it as next to the 5th, right? This is a 9 over 24. Honestly, you could leave it as a 9 over 24. If you want to cancel something, that's fine, but the more simplifying you do, the more likely it is you're going to do something wrong. I do need the ellipsis there because I'm skipping a whole bunch of terms to jump to the nth term. So 3n over n plus 1 factorial x to the 3n minus 1 dot, 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 dot. right? So that's fine. That's one way to do it. The other way to do it is you could write out the first couple terms and then differentiate them. So that's one option, right? The other option, right? So option 2, just to show you that you have option 2, right? So option 2 is write out sum of f of x, then derive. I don't care which one you pick, right? So unless you're required specifically to do one or the other, if you chose to do that, right, if you chose to write out sum of f of x, and I'll just go up to the top, I would probably have picked the first option, but it's up to you. So let me just steal this for a sec, and let me show you what I mean. So another completely okay option, and again, it's the end result that we want, so whichever one you like better, right? If you wanted to do this, you could plug in and write a couple terms of f of x. So you could plug in n is 0, and you're going to get 1 over 1, right? And then, so this was n is 0, right? And then you could plug in n is 1, and if you did that, you'd get an x to the third over a 2 factorial, right? And then you could plug in n is 2, and you'd get an x to the sixth over 3 factorial, and you could plug in n is 3. And the reason I'd go as high as n is 3 is I know that when I differentiate, this term's going to be gone, right? I can see that because it's a constant. This is a constant. So this is definitely going to derive to 0. So I know I need 3 terms, so I go 1, 2, 3. When I plug in n is 3, I'd get x to the 9th over a 4 factorial plus dot, 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 and then I know it's an x to the 3n over an n plus 1 factorial, right? Then I could derive, right? So that's one option, and then you could say, cool, now that I know that, then I'm going to derive, I'm going to differentiate, right? And get that f prime is 0, which we saw before, right? When I drop the power down in front, I'm going to get a 3x to the second over 2 factorial, right? When I drop this down in front, I'm going to get a 6x to the 5th over 3 factorial. When I drop this down in front, I'm going to get a 9x to the 8th over 4 factorial, plus dot, 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 dot. I'm going to get a 3n over this n plus 1 factorial times an x to the 3n minus 1. And it's the same answer, right? So I just want to show you that red answer is the same answer that I got up here in black. Whichever way you want to do it is fine. The idea is that you're differentiating an infinite series. All right, go ahead and give P2 a try. Same idea. I don't care if you want to just find the general term first and then figure out the derivative from there. It doesn't matter, right? So option 1 is to just say, hey, you know what? I'm going to straight up go ahead and differentiate this the way it is right now. F prime is going to be so this is going to be the sum from n is 0 to infinity of, I drop the power down in front, so this 2 to the n, I'll multiply by an n plus 1 over an n plus 1 x to the n, because it would be n plus 1 minus 1, right? Well, these guys cancel, and I'm pretty sure I just get that this is a 2n times x to the n. So I think I'm going to get that f prime of x, the first term is going to be a 0, right? When I plug in 0, or sorry, the first term is going to be a, my bad, the first term is going to be a 1. My bad, first term is going to be a 1, because this would be 2 to the 0 and x to the 0, so I get a 1, right? Second term, so that was when I plugged in n is 0, right? When I plug in n is 1, I get a 2 times x, right? When I plug in n is 2, I'm going to get a 4x squared. And the other way to see this, if you like this better, you could write this as a 2x to the n, right? When I plug in n is 3, I'm going to get an 8x squared, blah, 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 blah. Sorry, 8x cubed, my bad. All the way up to a 2x to the n, right? So that's fine. And I was only asked for the first 3 non-zero terms, so I could write this as 1 plus 2x plus 4x squared plus da-da-da-da-da, 2x to the n. And that's fine, right? So that's one option. The other option is you could write out the first couple terms and see what happens, right? It's the same idea. It's just a slightly different way to do the same problem. I don't have a preference. The AP Gen really doesn't have a preference. As long as you do stuff correctly, nobody really cares. So option 2, right, is write out sum of f of x, then differentiate, right? All right, so if we did that, right, if I started with plugging in n is 0, right, I'd get 1 over 1 times an x to the first, right, that's when n is 0, right, and when I plug in n is 1, I get a 2 over 2 x to the second, and when I plug in n is 2, I get a 4 over 3 x to the third plus da-da-da-da-da. And then when I plug in n, I would just get 2 to the n over n plus 1 times x to the n plus 1, right? Then if I differentiate, you'll see I get the same answer I got before, right? Because when I differentiate, notice that this was just an x plus an x squared plus a 4/3 x cubed, right? Et cetera, et cetera, et cetera. So when I differentiate, I get a 1 plus a 2x plus a 4x squared, which is exactly what I was expecting to get. And then we've already seen that this cancels to just give me 2nx to the n, or if you prefer, 2x to the n, okay? So either way you choose to do it, same idea. All right. So this one's tricky. We're going to write the second degree Taylor polynomial. Notice that I'm not asking you for the nth term. That usually means that we're looking at a situation where we're going to have to divide or multiply an infinite series, so you can't actually give me the nth term. So the trick here is that we know the series for sine x, right? We know the series for sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. Okay? We know the series, so if I rewrite this for a second, if I rewrite this as a 1 over 1 minus x times a sine x, because that's what this is, we also know the series for this. The series for 1 over 1 minus sine x, this is a geometric series where a is 1 and r is x, right? Because it's a over 1 minus r. So this is 1 plus x squared plus x cubed, da 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 da. So what you're essentially doing is multiplying the blue series times the red series. So f of x, right? So f of x is equal to my blue series, 1 plus x squared forever, okay, times my red series, which is x minus an x cubed over 3 factorial plus da 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 forever. The trick is that I only want, okay, so remember that here's the tricky part, right? I can't FOIL this infinitely, right? I can't distribute / FOIL infinite terms. It's not possible. So I wasn't asked to do that, and that's kind of a trick, but you can see I was only asked for the second degree Taylor polynomial. There's a reason for that, right? I was only asked for the second degree polynomial because, so we only want terms degree 2 and lower, right? Because that's what a second degree polynomial would have. So when I distribute this, I can instantly knock this guy out because he's already over a cube, right? Or over a squared rather, right? And the trick is I can also knock out this guy because the first thing I could multiply him by is, that's a cube, right? That's an x cubed, so he's already knocked out. So basically, when I distribute, I'm able to distribute the 1, but only to the first term, right? So I'm able to say, hey, this f of x should be approximately the 1, but I can only distribute the 1 to the x because anything higher than the x would give me a term higher than squared. So 1 times x, which is x, right? And I can distribute this x, but only to the x. So I'm going to get this. That's it, right? Plus a bunch of other stuff, but we don't know what that other stuff is, right? Like, this is all I can distribute to have a second degree Taylor polynomial. So I said f is approximately because that's not the whole f. So my p sub 2 of x, the second degree Taylor polynomial, is going to look like this. That's all the second degree, first and second degree terms and constant terms, okay? So that's the idea, right? So we're going to go ahead and, again, that's a trick question. We weren't asked to use it. Sometimes we're asked to use it. We weren't in this case. So here we did exactly what we were asked. We found the second degree Taylor polynomial. We called it p sub 2, and that's it. All right, so you're going to do a similar one. This is the same basic trick question. Again, notice you're only asked for the second degree Taylor polynomial. You're not asked to do anything else because you can't FOIL infinite terms. So yet again, the trick is going to be that we have two infinite series, both of which we have memorized. We know the infinite series for the red thing. We know the infinite series for the blue thing. This is going to be 1 plus x squared over 2 factorial plus da 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 forever, right? This guy, oh, and if it helps, let me actually add one more term. I want to go one term farther than I would normally have to go because I want, oh, sorry, meant for that to be red, because I want you to see that you intentionally stop using them once they become too big to meet the restriction in the problem, right? The restriction is a second degree polynomial. Cosine, right? Cosine is a 1 minus an x squared over 2 factorial plus an x to the 4th over 4 factorial plus da 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 forever, okay? But remember, I'm looking for a second degree Taylor polynomial. So as I distribute, anything that would give me higher than a second degree is automatically out. So I'm going to multiply this 1 by this guy and this guy, because that would, so what I'm going to get for my second degree Taylor polynomial, right? I'm going to get a 1 times 1, great, and I'm going to get a 1 times a negative x squared over 2, because that's what 2 factorial is. So this guy's done. Then I'm going to say, hey, can I distribute this positive x? Well, I can do x times this guy, But I can't do x times the x squared because that would be an x cubed. So x times 1 gives me a plus x. Cool. Okay, but I can't do x times this guy because that would be a cubed. So this guy's done. And then I look at this x squared and I say, okay, cool. Can I multiply the x squared times anything? Well, I could do x squared times this 1, but not x squared times anything higher because that would give me higher than s squared. So I'm going to get that this is plus an x squared over 2 because that's what 2 factorial is. So if I clean this up a little bit, I get that my p sub 2 of x seems to be a 1 plus an x, and then there is no second degree term because these are the same thing but opposite signs, right? So that's it, right? So there's no x squared term because its coefficient is 0. And that is what it is. So it turns out that my second degree Taylor polynomial actually is the same as my first degree Taylor polynomial. So in this case, p sub 2 of x is actually the same as the first degree Taylor polynomial because there is no second degree, right? All right, moving on. So, given the power series of the function f, show that f is a solution to this diffie-q. Now, this is tricky, right? So, basically, we know that I could plug in this power series for y, and I could plug in the power, I'm trying to show that I could plug in the power series of this thing for y prime, and I could get sine of x. So this is a little bit tricky. It's a little bit outside the box. It is the kind of thing that an AP could ask on a free response. So let's find the power series for f prime of x. The easiest way to do that, and remember when you're looking at this, that you can write this as just the coefficient, 2n plus 2 factorial. You can write that as the coefficient of your x term, right? So that's fine. So f prime would be the same negative 1 to the n. Oh, I forgot my summation. Hang on. F prime would be the summation from n is 0 to infinity of this same negative 1 to the n, right? But I drop the power down in front and then reduce the power by 1, right? And I'm going to get that this is so down here I have a 2n plus 2 factorial. Okay, so that's what this is going to look like. So basically what's going to happen, right? So that's what my f prime is. That means that x times f prime of x, right? If I put an x in front of an f prime of x, because that's what's happening here, right? X times f prime of x is just going to multiply an extra x in here, right? So what it's going to do is it's going to end up making this the sum as n goes from 0 to infinity of a negative 1 to the n times a 2n plus 1 times x to the 2n plus 1, because there's an extra x, right? There's an extra x being multiplied in front of this thing, all over that same 2n plus 2 factorial. So the question is, if I add these two series, so if I add x f prime of x, which we just found the series, plus f of x, do I get sine x? Right? That's the question, right? So let's see what happens when we add these two series, right? So this series here is a negative 1 to the n times a 2n plus 1 x to the 2n plus 1 over a 2n plus 2 factorial, right? This guy we were given was a negative 1 to the n x to the 2n plus 1 all over a 2n plus 2 factorial. And in both of the cases, so the whole thing, so I'm going to put them all in one series, right? They were summing from n is 0 to infinity. I just kind of ran a space. And the question again is, does that equal sine? Right? That's what we're trying to show. So there are a couple ways to do this. You could write out some terms and see what happens. I'm going to make an argument, so it's fine if you want to write out some terms and see what happens. I'm going to argue that you can see that there's a couple things going on here. Number one, there's definitely a GCF of this negative 1 over n and the 2n plus 2 factorial, right? I'm going to argue that that's there really clearly. That's a GCF. These guys both have it. They both have this in the denominator. I can factor that out. When I do that, I have a 2n plus 1 times this quantity, right? So I have essentially 2n plus 1 times x to the 2n plus another 1, so 2n plus 1 times x to the 2n plus 1 plus another 1 times an x to the 2n plus 1. Well, I'm going to argue I could actually take out another GCF. I could argue that I could take out the x to the 2n plus 1. So if I did that, I'd get that this is the sum from n is 0 to infinity of a negative 1 to the n, a 2n plus 2 factorial, and an x to the 2n plus 1, right? Because there's definitely a GCF of x to the 2n plus 1, right? And what's left seems to be 2n plus 1, sorry, I wanted to switch colors, 2n plus 1 again. Well, that's a 2n plus 2. So what I want you to notice is what happens is I can take this thing and recognize that this is actually a 2n plus 2 times a 2n plus 1 factorial. Well, these guys can be canceled, and I end up getting that this is the series from n is 0 to infinity of a negative 1 to the n, x to the 2n plus 1 over a 2n plus 1 factorial, which is definitely the series for sine. Right, this is the series for sine, right? If you plug in starting at n is 0, you're going to get an x minus an x cubed over 3 factorial plus an x to the 5th over 5 factorial, dot, 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 and that's definitely the series for sine. So that's the way I would do it. There are other options. You also could have listed a bunch of terms out and seen that what happens is that they would combine in that way, and that's also totally fine. This is definitely a think outside the box kind of problem, but I stole this kind of question directly from the AP, so it's the kind of thing you could be asked to do, right? You could be asked to see that this is a solution to this differential equation. All right, let's go ahead and do another one. All right, so let's try another one. Same idea. We're going to show that this series is a solution to this diffie cube, right? So what we're going to need to do first is we're going to need to find the f prime of x series, right? So that's going to be the sum from n is 0 to infinity of. When I differentiate, again, if it's easier to see this, this is a 1 over an n plus 1 factorial times x to the n, right? So when I differentiate, it's going to become n over this n plus 1 factorial, x to the n minus 1, right? Which means that this expression, right, so let's color code a little differently, this expression, which would be an x times my f prime of x, would just be the same series I just got, but multiplied by an x, right? It would be n equals 0 to infinity of n over n plus 1 factorial, x to the n minus 1 times an x, so together, these guys are just going to become an x to the n, right, because it's an n minus 1 plus 1, right? So, again, I get that this is the sum from n is 0 to infinity of n times n plus 1 factorial x to the n, right? And then I know this sum, right? So this guy is this sum. So the question is, can I show that the red sum I have plus the green sum, can I show that this thing, the sum from 0 to infinity of n over n plus 1 factorial x to the n, plus the green sum, which was the sum from n is 0 to infinity of a 1 over n plus 1 factorial x to the n, can I show that this thing is equal to e to the x, right? Well, if I put these together, because they're the same sigma, so I can put them together in the same space, right? If I put this together and this together, you'll notice that I can factor out both an x to the n and an n plus 1 factorial. When I do that, what seems to be left, right, because I factored out this and the n plus 1 factorial on the bottom, what seems to be left is an n plus 1. Well, this denominator, right, this guy right here, sorry about that, is actually an n plus 1 times an n factorial, right? So I could cancel the n plus 1s. So I get that this is the sum from n is 0 to infinity of x to the n over n factorial, which is absolutely the series for e to the x, right? And you can see that because that would be a 1 plus x squared over 2 factorial, etc. And this side would also be the same thing, right? 1 plus x squared over 2 factorial, etc. Dot, dot, dot is what I meant there. So they're the same, and it is a solution. So just kind of showing you how that works. Again, it's not wrong if you wrote out a bunch of terms. I personally probably wouldn't, but it's certainly not wrong if you said, hey, I'm going to write out some terms for the f. I'm going to write out some terms for the f prime and see what happens. All right, let's keep moving. All right, so f prime of x, so we're given f prime of x, and we're given the value of f of 0. We're going to write a power series for f, including the first 4 non-zero terms. Okay, so the trick is I should start by writing a power series for this, okay? So in order to write the power series for this, I need to use one of the power series that I should hopefully remember, okay? So I remember that 1 over 1 minus x, right, is essentially geometric, where my a is 1 and my r is a negative x, right? Well, that series looks like this. 1 plus x squared. Oh, sorry, my r is a regular x, my bad. 1 plus x squared plus plus x plus x squared plus x cubed, etc., plus da 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 x to the n, right? So I look at this and say, hey, that's the same series, but now my x is an x to the 6th. So my f prime of x series should look like a 1 plus an x to the 6th plus an x to the 6th squared, which would be x to the 12th, plus da 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 da, an x to the 6th to the n, right, which would be an x to the 6n. So this series is essentially the sum from n is 0 to infinity of x to the 6n, right? That's what this f prime would be. So if I want the series for f of x, I just need to integrate, right? So my f of x is going to be what happens if I integrate this thing, right? So I'm going to get an x, right, plus, and we do technically have a c, but we'll deal with that in a sec, right? So there's this constant when we integrate, right? When I integrate the 1, I'm going to get an x. When I integrate the x to the 6th, I'm going to get an x to the 7th over 7. This will be an x to the 13th over 13, plus da 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 da, x to the 6n plus 1 over 6n plus 1, da 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 da. But since we know, right, since it's known that f of 0 is 0, right, f of 0 is 0. F of 0 is 4, my bad. Sorry, f of 0 is 4. That tells me what my c is, my bad. Miscopied, thought f of 0 was 0. Since we know f of 0 is 4, that tells me that's my c, right? So f of x is going to be 4, right? Because if I plugged in 0 for x, all of these terms are knocked out, right? So I'm going to get 4 plus x to the 7th over 7. Now let's see how many terms we were asked for. First, 4 non-zero terms. So that's 1, 2, 3. I need the x to the 13th over 13 plus, and then the general term, x to the 6n plus 1 over 6n plus 1. And that's what I needed, right? 1, 2, 3, 4 non-zero terms, and then the general term. All right, try the same thing. So we're given f prime, and we're given that f of 0 is 10. Let's go ahead and find the power series for f. So the first thing we need to do, right, is essentially you could either use your memory that the series for 1 over 1 plus x was where a was 1 and r was a negative x. So this alternates. It's 1 negative x plus x squared minus x cubed, etc. Right? A negative 1 to the n x to the n. That's fine, right, if you want. Or you could actually just jump right to recognizing. So if you did it this way, you're just replacing the x with an x squared. The other way to do it is to just recognize that a negative x squared could be your a. It doesn't really matter. So my f prime of x is going to be, instead of anywhere I saw a anywhere I saw an x, rather, I'm going to put an x squared, right? So this is 1 minus x squared plus x to the 4th, because it's x squared squared, minus x to the 6th, because it's x squared to the 3rd, plus da 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 da, negative 1 to the n, and then this is x to the 2n, right, because it's x squared to the n. That's fine, right? And then when I want to find f, right, my f of x is going to be what happens if I integrate this. So I have a constant, right, and then this guy is going to become a plus x minus an x cubed over 3, right, plus an x to the 5th over 5 minus an x to the 7th over 7 plus da 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 da, negative 1 x to the 2n plus 1 over a 2n plus 1 plus my ellipsis to say it goes on forever. Now I was given that f of 0 is 10, right? F of 0 is 10. So that's my c, because if I plug in 0, right, if x is 0, these all get knocked out. So this must be my 10, right, because f of 0 is 10, right? So I'm going to get that f of x is, and then when I go back up, I see how many terms they want. They want the first 4 non-zero terms and the general term. So I'm going to get 10 plus x minus an x cubed over 3, that's 3 terms, plus an x to the 5th over 5, that's as far as I need to go. And then the general term will be a negative 1 to the n, x to the 2n plus 1, I believe. Yep, okay, so 2n plus 1 all over an n, 2n plus 1, and then the ellipsis. And that's my answer. Notice how so many of these build on those basic Maclaurin series that you need to memorize. All right, so we're going to write the first 4 non-zero terms and the general term of the Maclaurin series for this. So there's actually a bunch of things going on here, okay? So the first thing I need to do is I need to write, I need to recall, so this is memory, right? I need to recall what the e to the x series is, right? It's a 1 plus an x squared over 2 factorial plus an x cubed over 3 factorial, etc., up to x to the n over n factorial, right? Then I say, okay, cool, now I need an e to the 3x. Well, e to the 3x would be a 1 plus, and this is going to be a 3x, right? And then this will be a 3x quantity squared over a 2 factorial, right? And this is going to be a 3x quantity cubed. Anywhere there was an x, I plug in a 3x, right? All the way up to a 3x to the n over n factorial. Okay, that's fine. So now you might say, okay, cool, but what do I do about the minus 1 and the over x? Well, if I take this red thing minus 1, what I want you to notice is that my f of x is going to be this entire red series. Okay, so this f of x is going to be the whole red series that I just wrote out, right? So it's going to be a 1 plus a 3x plus this 3x quantity squared over 2 factorial plus, what did we say first? 4 non-zero terms, 3x quantity cubed over 3 factorial. So I'm actually going to need another one. We're going to need 3x the fourth over 4 factorial. Okay, up till forever. Minus a 1, right? Minus 1 all over an x. Okay, well, there's a plus 1 and a minus 1. They're just going to go away. And what's going to happen, I guess I should have left my nth term in there somewhere, but that's okay. I kind of ran out of room. So what's going to happen is those terms are going to sum to 0, and now coincidentally, everybody has an x. So I have a 3x, right? I have a 9x squared over 2 factorial. I have a 27x cubed over 3 factorial. I have an 81x to the fourth over 4 factorial, and I have way down the road somewhere, I have a 3 to the n, x to the n over, sorry, I don't need that parenthesis. Way down the road somewhere, I have a 3 to the n, right? 3 to the n and an x to the n and an n factorial, right? Dot, 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 all over an x. Well, because x is a monomial, I can divide each one of these terms by that monomial, right? So basically, I'm going to get that f of x is x divided by x is just going to give me the 3, right? Essentially, it's going to lower all these powers by 1. So it's going to be 9 halves x to the first, right? It's going to be 27/6, and honestly, I'm going to leave it as 27/6 or even 27 over 3 factorial because there's no incentive not to. X cubed, right? I'm going to leave it as an 81 over a 4 factorial because there's no incentive not to. Dot, 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 and then my nth term is still going to be a 3 to the n, but it'll be an x to the n minus 1 over that n factorial. And that's it. So the trick is that there's a lot going on. You have to know the basic series for e to the x. You have to be able to plug in the 3x, right, to figure that out. And then you have to be able to simplify with that minus 1 and all divided by x. So this is a pretty realistic AP problem. So we should get used to this concept. Notice that I don't care if you can do it in your head. If you can jump from this to here in your head, that's fine, except you're getting almost no AP credit. It's not a judgment fact. It's not that I don't think you're doing it if you can skip to that spot. The point is that the AP is giving you points for communicating understanding. So on an AP free response, they're probably going to give you a point for this. They're probably giving you a point for this. And then they're probably giving you 1 to 2 points for the final answer. This is probably a 4-point problem, and you're probably losing half of those points if you just skip to the end. So please show steps along the way. Clearly communicate in your steps which series things are. Don't just write a series. Write that this series is e to the x. Don't just write a series. Write that this series is e to the 3x. It's important that we communicate clearly. We want to communicate understanding because the AP is basically free college credit, and it's dope. So please communicate understanding. All right, let's do one more like this, and then we'll do some quick multiple choice. We're going to write the first 4 non-zero terms. This is the same basic idea, right? So we're going to look at this and say, wait a second, I should start with the basic cosine function. Right? So the basic cosine of x is 1 minus an x squared over 2 factorial plus an x to the fourth over 4 factorial minus an x to the sixth over 6 factorial. Now I see that I want the first 4 non-zero terms, and having done this a bunch of times in the past, I recognize that this 1 is going to disappear. So I'm going to make sure I go up at least to x to the 8th over 8 factorial plus dot 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 x. So this is a negative 1 to the n, x to the 2n over a 2n quantity factorial. Right? I then say, cool, I don't just want the basic one, I want the x squared one, right? So that means that cosine of the quantity x squared is all of these same things, but with the x squared. So that's going to be a 1 minus an x to the fourth over 2 factorial, right? Plus an x to the, if you do x squared to the fourth, you get an 8, right? So x to the 8th factorial. This will be, oh, that's a minus, my bad. Okay. So minus an x to the squared to the 6th would be 12th, right, over 6 factorial, plus squared to the 8th would be 16, so x to the 16 over 8 factorial, plus dot, 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 dot. You still have the alternating, but it's now going to be x to the 4n over the 2n quantity factorial. Okay, great. Now I need to take that entire red thing, subtract 1, and divide everybody by x. So what that means is that my f of x is going to be this crazy red series, right? So 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial minus x to the 12th over 6 factorial plus x to the 16th over 8 factorial plus dot, 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 negative 1 to the n x to the 4n over the quantity 2n factorial, right? That thing minus a 1 all over an x. Well, just like we saw before, it's not an accident. This one and this one are magically going to disappear, and now everybody has an x, right? So once they disappear, everybody has an x. So dividing by x is just telling me to lower each x value, or each x power, by 1, right? Because I'm dividing by x to the first. So my f of x is going to end up being, instead of an x to the 4th over 2 factorial, it's going to be an x to the 3rd over 2 factorial. It was negative. Instead of being an x to the 8th, it's going to be an x to the 7th over 4 factorial, right? Instead of being an x to the 12th, it'll be x to the 11th over 6 factorial. Instead of being an x to the 16th, it'll be x to the 15th over 8 factorial. And then dot, 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 negative 1 to the n, it'll be an x to the 4n minus 1 all over this 2n factorial. And that's it. Right, so that's what they want. Again, this is probably a 4 to 5 point problem, and you're getting points for the steps along the way. If you blow them off and just jump to the end, you're going to lose a lot of credit. Please communicate understanding. Please make sure that every time you write a series, you label what that series is. Is that series cosine x? Is it cosine of x squared? Is that series the entirety of f of x? Please make sure you do that. And also notice, and I should have had an ellipsis at the end of all of these, if you're saying that f is equal to this, it does have to be the infinite series, which means that it has to have that ellipsis at the end. All right, let's do 2 multiple choice, and then that'll be the end of this video. And this is technically the last section in AP BC Calculus. We will have a couple other videos. We'll definitely have a lot of videos for AP Review as well, but this is our last section in AP BC. All right, so the given series converges to one of the functions below. Which one? So basically, this is saying this series matches something else. Which one could it be? So you know it's a sine, right? So if it were this one, right? So let's start, let's walk through this, okay? So here's what I know, okay? The first thing I notice is that it's not a 2 everywhere. So like this one, right? This one would be a 2 in front of, so generic sine, right, is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, dot, 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 dot. If you put a 2 in front of it, it's just going to multiply everybody by 2, right? So, oh, sorry, I forgot to cube it first, my bad. So it's definitely, so there's a couple things going on here. So if I put a cube in there, right, if I do sine of x cubed, then it would be an x cubed minus, now I'm going to cube the cube, right? So it's going to be cube. So this would be an x to the 9th. Well, the first thing I notice, I see this 9, and I'm like, oh, hey, it's not a 9, right? Like this guy's not a 9. This is a 9. That kind of rules out the 2 that have cubes on the inside. Because if there's a cubed on the inside, this second term is going to be x cubed, which is a 9. That's an x to the 9th. And I don't have an x to the 9th, so those 2 are out. Okay, so then it's possibly one of these 2, right? Well, so I can rule out those 2. When I go to look at these 2, I say, okay, well, if the 2x is on the outside, this would be 2x squared. This would be a 2x squared times an x minus an x cubed over 3 factorial, blah, 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 blah. It falls apart by the second term. So the first term is right, I get a 2x cubed. But the second term is a 2x to the 5th over 3 factorial. So I get a 2 here. Well, look at what the actual answer has. It has an 8. Okay, so it's not this one because the second term is wrong. So it kind of means by default it has to be this one, but we can actually walk through the logic of why, right? This would be an x squared times, when I plug a 2x into my sign, I get a 2x minus 2x quantity cubed over 3 factorial plus dot, 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 dot. Well, sure enough, if I distribute, this is a 2x cubed, check, and this would be an 8x cubed times that 2. So sure enough, there's that negative 8 that I want. It's definitely C. When you're handed a problem like this, you want to walk through the series that you're given and try to cross them off until you find the right one. You shouldn't construct all of these series. You should say, hey, there's a couple different options. There's an option where x cubed is on the inside. Does that pan out? No, it doesn't. And then you can cross off all of those. So go ahead and give P7 a try. Same idea. We want to see what this converges to. So A couple things to notice. The first thing to notice is that these signs alternate. The signs alternate, and e to the x is all positive, right? It's all positive values. So, see how this is all positive? So I can cross off any answers that don't introduce a negative into this problem, right? I can cross off any, oh, my bad. I can cross off any answers that don't introduce a negative because these would be all positive values and these would also be all positive values. So it has to be one of these two, right? The next thing I would do is I'd probably look at this easiest one and say, hey, if I introduced a negative 3x, e to the negative 3x would be a 1, right? And as soon as I see that it's a 1, I say, oh, that's the wrong answer because I'm supposed to start with an x. E to the negative 3x would be a 1 plus a negative 3x, right? Plus a negative 3x quantity squared over 2 factorial. So that's not right. And I can pretty much at that moment say, oh, hey, since that's not right, it's got to be answer B, but let's see why it's B. For B, if I did x times the e to the negative 3x, it would be an x multiplied by this entire messy thing, right? This is a 9x squared over 2 factorial, blah, 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 blah. If I distribute the x, I'm going to get an x minus a 3x squared plus a 9x cubed over 2 factorial. Let's check if that pans out. And hey, there it is. So it's answer B. So that's it. This is our last official lesson video. We'll have some other videos, but you have made it through AP BC Calculus. Congratulations.